So today we talk about mainly recurrent neural networks, and which are the networks typically used for language processing, natural language processing. So the way these networks work is that they expect to take as input ordered data. So you have a sequence of data. This sequence could be the words in a sentence arranged according to the grammar, but it could also be a time series. For instance, it could be monitoring data from some hardware equipment. It could be some sensor reading, I don't know, heartbeat or some such. It could be data from a telescope and so on. And so the way this works that the network reads in at, let's think about the time series at different timestamps. And the processing of each time step depends on what's read in, but also on the outcome of the processing of the previous one. So these networks typically work with two outputs. So there is an X that comes in and there is a Y that gets out, but there is also an H. H is effectively, it's the content of some memory cell, which is carried on across the network. So you will see that what changes in the networks is what happens in that purple blob, which is the network architecture, the unit architecture. And effectively, you will see that there are a lot of things that we didn't use so far that much, which are hyperbolic tangents and sigmoids, because effectively these things work with the idea of putting gates, memory gates, that decide when to retain and when to delete information from these memory cells that is incorporated by the H. And then you can decide to make the sequential processing depending on H or on Y. Basically, you are trying to really mimic the persistence of information in memory as in a brain. And the advantage of this network is that whenever you have a data set which doesn't have a fixed size, like a time sequence, this network can process that, as opposed to convolutional networks that need like the full length of the data set to be specified ahead. Now, in particle physics, of course, you can say that you don't really see a use case for this because thinking about colliders, but I think it's true also for underground experiments. There is no concept of sequentiality. There is no time information in the time of arrival of informations to a large extent. Each collisions in the LHC is independent of what happens before or after to a very good level of approximation. So it's not clear that you would say this is something good for particle physics. On the other hand, the big advantage is the fact that you can process arbitrarily long networks, sequences. So in some sense, this is a plus. And also the fact that it's an alternative approach to the CNN, which, as we discussed, somehow requires that your data comes from some regular geometry. There is a cost. The cost is in the fact that there is an underlying assumption that there is an ordering principle that lets you decide what goes first and what goes after. And then there is a practical thing that the processing is sequential, so these things are typically slower. So, for instance, if you're thinking about triggers, it's not necessarily a good thing to do. So the main idea behind is that when you're given a time series or a sequence of words, the order is somehow encoding what's going on. And the ordering has a lot of information in terms of the kind of the context, the meaning of a given sentence. So basically, what you do is that processing the sequence, you basically try to understand the meaning of the sentence, considering that the order came directly straight from the grammar. And you can do the parallel of these thinking about jets, where if you have an ordered list of of jet constituents, the underlying grammar is QCD, and you're trying to learn things about the jet based on that. Now, which order would you use? I mean, it's not that there is a clear answer, but on the other hand, we face the very same problem when we deal, sorry, one sec, when we deal with Parton shower Monte Carlo, when we deal with jet clustering. So there are metrics that can be used to order the particles. And so the idea behind is that particles are your words and QCD is the grammar. And so in the case of our example, what you do? You should now process the sequence, an ordered sequence of particles, and each particle would be represented by its own features. The features could be pt, eta, phi, could be px, py, pz, could be both, as we discussed 2 days ago. But could also be other things like the electromagnetic charge, which kind of particle it was, and so on and so forth. And then processing the sequence, you can try to answer the same kind of questions that we've been dealing with so far. Now, nothing says that you should do this only for jets. You could consider doing this only with the whole event. Like you could take the full list of particles, and instead of clustering jets as we usually do, you would give it to a network of this kind. You could ask which kind of event was this, and I will show you an example later at the end of this lecture. Now, so I personally explored this direction at some point, and at that time it was really an attempt to try to go away from the geometrical constraints of a convolutional network. As of today, let's say it was an intermediate step, but it would not be my best option. I think that graph networks eventually in literature emerged as a more suitable architecture to do this. And the advantage of graph nets, we'll see tomorrow, is that you remove the need of the ordering principle, and then you can process just an unordered set of items. Now, back to the recurrent network. So there are 2 ways you can operate them. You can inject a sequence with the idea that you get out a sequence. And the sequence you get out could be the memory state of each cell, could be the Y of each cell, and so on. So, and things go in and things go out. Or you could just focus on the outcome of the last iteration. And then in that case, you come in with a sequence, you get out with a number. And this is done, for instance, in Keras with this return sequence option. Now, typically what you do is that you just don't operate one of these kind of things, but you have n of them stacked. The same way we had nodes in a dense layer or kernels in CNNs, we have units, recurring units into an RNN. So the very first option parameter of your RNN allocation would be how many units you want to allocate. Then you would say, you will give all the other parameters of the network, which kind of activation function and so on. So there are several architectures. So recurrent networks, to some extent, are a paradigm, but then there are different realization of recurrent networks. And so this is an example. I didn't say that before. Unlike convolutional networks, these are not feed-forward neural networks in the sense that the input is processed sequentially and not at one shot. Okay, so you don't have input in and output, but you have that the output depends on the input. Sorry, the output of one iteration depends on the input, but also on the output of the previous iteration. So it's not a feed-forward architecture. And then on the what the different flavors of recurrent networks are different because they have different architecture in the purple blob that you were seeing before. So historically, people talk about, so in the top right, you see, for instance, those that are implemented in Keras. We'll be mainly playing with GRUs in the example, but you could use the simple RNN or the LSTM as well. The simple RNN, I mean, before the others appeared, there were just RNNs being Hellman or Jordan networks, are the simplest realization of the idea. So where the structure the structure that is in the blob is the equivalent of a shallow neural network, like a single layer kind of operation. Then in 1995, LSTMs came, and as of today, I would say they are the most popular and well-performing choice for serial data processing. Recently, GRUs came in, which are, they add something special on top of LSTMs, which is not only they have a mechanism to remember things, but they have also a mechanism to forget things. And we will see that. So there is a gate that decides how much information from the cell memory cell should be removed. And so what is passed in the memory cell is a combination of what's kept from the previous iteration and what's learned from the iteration that is happening at that specific moment. Now, I will go quickly on these slides in the sense that it's just to let you get a feeling of what's going on with these networks, but you will see that there are a lot of very arbitrary choice made. So it's not like there is a ruling principle that says this is the thing you should be doing, but it gives you an idea of how they work. So this is the simple recurrent network. And as we said, there is something which is coming from the previous iteration. There is the new X that you are loading. And then you take these two quantities and you compute the memory cell state H and the output Y. And there are two ways of doing that, which are the Hellman and the Jordan networks. You see them on the top right. And the only difference is what gets multiplied by the U weights. So the algebra is very similar to that of the dense network if you look at it. So what's happening is that, let's take for instance the Hellman network. The memory cell comes from some sigmoid activation function. So it's a number between 0 and 1, for instance, if you use a sigmoid, of the input multiplied by the weights, the memory state of the previous iteration multiplied by its own weight, and some bias. And the output is the same thing, but it doesn't depend on the input. So the memory is updated based on the X and the H, while the Y is only updated based on the H. And if you look at the Jordan network, it's the same thing as except that the new H depends on Y and not on H. But it's two different choices you can make. And then the thing that that you typically do is that these basically are gates, are memory gates. So you want to have activation function which are sigmoid-like. Now, LSTMs, here you see it is way, way more complicated. I would try to give you a sense of what they are doing, but I would not try to speculate too much on the meaning of it, in the sense that you could decide to do something else, and it's an empirical fact that these things work very well. So the idea, as usual, is that there is some information is flowing through the memory cells of the network, and basically you use these gates, which again are ruled by sigmoid function, which are functions of the new input that you get in, to decide if you want to update or not the memory. And this is done in layers. So this is again, it's a deep version of a plain recurrent network. Whenever you have a yes or no answer, you basically put a sigmoid function. You can use other function like hyperbolic tangent. You could use hard sigmoid, which is basically it's the function. But the sigmoid is a typically traditionally used choice. So the first layer is the part that you see highlighted there. Takes as input the new X, and based on that and on the current states of H, decides through a sigmoid if the weight has to be updated or not. It's the C that you see flowing on the top. The second layer takes the very same inputs, and the kind of circuit that it goes through is a little bit different. Again, you have a decision, so a sigmoid, if you want to pass the value or not. And the actual value that you pass through is this C tilde t, which comes from hyperbolic tangent. So it's a number between -1 and 1. And then the last layer is the one that decides the outputs based on the outcome of the previous two layers. So you take some input C, and using an hyperbolic tangent, you force it in the range -1 and 1. And then you apply, so this is the HT that you see in the second row of the equations. And then based on that, you apply a sigmoid function again to decide which fraction of the cell contents is passed through. See that it's very unintuitive. I have to say that every time I look at it, I don't get really the feeling of why it's working, and certainly the experts have a much better idea. I'm certainly not an expert of recurrent neural network design, but as a matter of fact, this is this very, very convoluted way of operating through the sum series has very, very good effective results. The GRU it's something similar, except, so you see that, for instance, the first step is very similar. You take the x and the t, and based on a sigmoid, you compute the fraction of events, because it's a number between 0 and 1, that you want to carry on. But and the second layer instead, it's a forgetting gate, where you do the very same operation mathematically, but then you will see that in the next iteration, this R is used as the fraction of information that you want to remove, and R and Z are used together in the third layer, in which you decide the new memory cell information H. So what you do is that you combine, so effectively you are computing an hyperbolic tangent. As before, you want an output in -1 and 1. And the argument of the hyperbolic tangent comes from two places. It's a weighted function of the inputs, so it's W times X, plus the current content of the memory, HT -1, the previous iteration, weighted by its own coefficient that you learn, U, times, R times that, where that product, that is a element-wise product. So if you have two vectors, you multiply the first element of vector 1 with the first element of vector 2, the second with the second, third with the third. And for matrices, it's the same. And so what this is doing is that it's taking the new information and it's adding only a fraction of the memory cell, which comes from R. And then at the very end, the information which is carried on is a combination of what you had before there and this new H prime T with the Z -1 minus Z coefficients. So it's a little bit different than LSTM, because there is this double mechanism which is not there in the LSTM. Now, does it work better?
We have a question.
Yes. Sorry? There is a question.
Yeah, hi, thanks. Is the purpose of a forget gate the same as the purpose of a dropout layer in a DNN?
No, it's not really a regularization. It's not a regularization element. It's really, so what's happening is that it's a way, so the LSTM, the way it works is that at each iteration, you work with this double binary. You see that these graphs are two inputs and two outputs. And the LSTM basically works by updating what's in the H direction, okay? Here is different in the sense that not only you update it, but you somehow you downplay it with this R gate. So this R, which is this number between 0 and 1, when you multiply it, you multiply here, you decide that basically only a fraction of it should determine the new state of the cell. So if you want, it's really a mechanism to handle. It's a double mechanism to handle this memory. On one hand, you want to update your memory content from ht-1 to ht, and you do that taking into account what you had in ht minus what you have in h from the previous iteration and what you learned from the new iteration. What you learn from the new iteration is a function of the new input, but also of what was in there times this coefficient r. R somehow it's saying that it's downplaying the importance of the memory, if you want, the importance of the memory of the memory content with respect to the input, because it's a number between 0 and 1, so it's reducing the importance of u times h. And how much you want to you forget or not, so how much closer to 0 R is, depends on, again, the previous content of the memory and the new inputs. So it's really saying, it's not just updating information, but it's also saying that this update mechanism should happen with a forgetting mechanism in place. And it's qualitatively, it's the real difference between LSTMs. Now, does it bring quantitative improvement? It really, I would say that at this stage it's not obvious, in the sense that if you look at literature, GRUs are certainly the recent architecture which is competitive to LSTMs, but I have to say that LSTMs endure, in the sense that they're still state of the art, let's say. So maybe at the end of the day, you can see this as a program specific thing, and yet another hyperparameters to tune is which kind of recurrent layer you want to use. I have played very little with this. I wrote a paper using, you will see later, I will show you the results of what a study we had done using recurrent networks. We tried both, and eventually we used GRUs because they were better for our case. But for instance, everyone else, like the referees of the paper, complained that in their personal experience it was the other way around. I don't think that there is a real rule there. So, are there other questions? No. So I'll show you a little bit some application, but again, it's somehow, I think that here, more than with the CNNs, we are really trying to force our data into a structure that is not very natural for our data to have. But still, you can do interesting things when you're dealing with very, very long sequences. In our case, we consider this problem. So in the trigger of the experiment, we reconstruct particles. So we have what's called particle flow reconstruction in CMS. We reconstruct all the particles in the event. So you get this sequence, which typically have like 1,000 particles or so. And then typically a decision on you want to accept or reject this event is taken based only on some of the particles in the sequence. For instance, typical example, the trigger that is used effectively to do all the electroweak physics, so the single lepton trigger, you accept an event which has a lepton, muon or electron, which is relatively high PT, 15, 20, depending on the running condition, and isolated from the rest, and it's your proxy for the fact that there was a W decay in the event. So if there is a W and a decay, if the W decays to a lepton and a neutrino, the lepton should be relatively alone in its solid angle around it. And so what you look for is an isolated, what we call an isolated high PT lepton. If you do the math of which events you are selecting, you have very high efficiency in selecting W's in TT bar. So like 90 something, 99% of the TT bar would be selected. On the other hand, if you look at the composition of the data that you're saving, which depends on the cross-section of the individual process, you discover that 1 event out of 3 is QCD still. And this is not a trigger for QCD. So you are saving 1 event out of 3 that will be immediately rejected, the very first things that you will do offline when you're gonna go and select your TT bar or your W. This means that you are carrying on a third of your events to just throw them away. And so this is a major waste of resources that it's still unsolved because nobody's doing anything against it. And this is because people prefer to write down trash. I mean, it's not a QCD's trash, but in the context of the lepton of an electroweak data set, QCD is trash. Then if you want to study QCD, you would use another trigger. But these events, you're trying them, it's completely, it's junk. And this junk is taking a lot of resources. I mean, 30% of this trigger is comparable to the bandwidth of, it's comparable to the bandwidth of, I don't know, the SUSY program of CMS, okay? To give you a sense. So you would like to have an application that looks at the event and says, look, okay, this event, you decided that you should accept it, but I really think you should not. And you would like to do it in such a way that you stay efficient on TT bar and W. So we try to handle this with several ways. Like, okay, let's look at the full picture of the event and let's do a convolution neural network, or we tried like with the high-level features. We tried with some other kind of images that's called abstract images. I'm not gonna go into those details, but also we tried with the sequence. And so the idea of the sequence is that we order the particles. So we start from the lepton, and then we start from the lepton, and then we order the particles from the closer to the most far away from the lepton. And then we invert the sequence. This is an important thing that usually people tend to invert the sequence if the sequence is structured in such a way that the relevant information comes at the very beginning, because it's true that these networks have memory mechanism, but this memory mechanism is not like it's not like your memory. So there is some deterioration of information as you go along the sequence. So it's better to invert the sequence and to leave the most relevant things at the end. So what we did is that we start from the lepton, we order the particles from the closer to the most far away, and then we invert the sequence, and then we process it with the recurrent net. So we tried LSTMs, we tried GR2s, we tried plain RNNs. As I said, you will have an array of these recurrent units, and each of these recurrent units, we only look at the last number that comes out of the sequence. And so we form an array of objects, of quantities that we build out of the full sequence of particles. So each unit gives me a number, and this number is a function of the full sequence. And this basically, again, is an architecture that engineers features. Then I take all these engineered features and I just put it into a dense neural network, and as we did yesterday with a convolutional network, and we produce the output. So if you look at how things behave, you see two interesting things. First, high-level features outperform convolutional networks. Here, convolutional networks are really suboptimal because this is like the image of the full detector, which is huge, and there's a lot of pixels. Most of these pixels are empty. So the image is very sparse, and you don't really learn much out of it. Instead, high-level features means that I computed quantities which I know are relevant to separate QCD from TT bar from W, and I do a pretty good job with it. But the sequence does better. And then, which was even further interesting for us, when you combine, so if you look at the bottom right architecture, the recurrent network, at the end of the recurrent units, you get out with a vector of engineered features. You could imagine to extend this vector, adding there the quantities, the high-level features that you think are relevant. And if you do so, you're gonna exploit not only the features that were engineered, not only the features that you engineered, the physics engineered, if you want, but also the correlation between the two. If what the network learns is completely redundant with respect to those quantities, adding those quantities should not make a difference. If you see a difference, it means that the network is learning something that you didn't know, but you know things that the network didn't learn. And this is what's happening. And if you look at this rock curve, so you can basically find very easily a working point. For instance, you can define the signal efficiency that through positive rate is on the y-axis. So if you look at a signal efficiency of 99%, so just below the plateau of the rock curve, you can see that you would intercept the gray line at something like 10% background contamination. This basically means that you are, since, for instance, if you think about you want to select top quarks, which are a very small fraction of the events in your data set, sacrificing 1% of your signal, you would drop the trigger rate by factor 10. And basically, remember, the composition is this. A third of the events are QCD. If you can drop that 38% to be a 3%, then it becomes a negligible contamination. And the other interesting feature is to go and check which kind of physics is your network grasping. And we did this taking the score of this classifier, the recurrent classifier in the bottom right, and correlating the score to the features that we were giving to the dense neural network. So these are the features that we think are relevant to separate QCD from TT bar from W plus jets, and these are the features that typically one would use at the analysis level. And you see that the pattern that you extract pretty much resembles the physics that you expect. So you see that the one on the left, no, let me see. Yes, the one on the left is the TT bar classifier. It's correlated to everything which measure the jet activity in the events. While the one on the right, which is the W classifier, is anti-correlated with it, like number of jets. This is because when you have a lepton, if the lepton is alone in the event, most likely you have a W. If there are a lot of jets, most likely it's TT bar, where one of the top gave you a W. And this kind of behavior is understood by the network that is exploiting it. So this gives you a sense that these kind of things can work for the events that we do. But as I said before, we are a little bit trying to force it into the kind of architecture that we have. Okay. Now, I'll pause here. I have another couple of slides that I want to go through, but if there are questions, I think this is a good moment to ask. No? Okay. So I want to show you now something else which can deal with the same kind of problem, so with a sequence of data, but using the convolutional network paradigm. And it's what people call one-dimensional convolution. So how does it work? It's exactly the same behavior of the convolution, the two-dimensional convolution, except that you are doing on a one-dimensional sequence of items, and each item is characterized, let's say it's embedded in the sequence through a set of information, a set of features. So it's not, as we discussed yesterday for the image, this is not a one-dimensional input, it's a two-dimensional input. The second dimension is what yesterday we called the channel, okay? So in an image, you had the three layers of two-dimensional image, red, green, and blue. Here you have a one-dimensional sequence for each of the channels. Imagine for a particle, like your particles are embedded in the sequence as pt, eta, and phi. You will have three channels, the pt channels, the eta channel, and the phi channel. And each channel will be a one-dimensional array, which corresponds to the sequence of particles, okay? Now, you can process this with the recurrent network, as we said, but you could instead use the same architecture that we had yesterday with the convolutional 2D, except that now the kernel is one-dimensional. So it's not a 3x3, 4x4, 5x5, but it's, for instance, in this case, 4x1. And the kind of math that you go through is the same. So you sum across the elements, you sum across the channels, and what you're summing is the product of the x that you read an input and the weight of the filter. And then you add a bias, you apply a convolutional, an activation function, and then you promote the output, the thing in the output. And then, for instance, you could imagine that at the end of the game, in this case, I considered, I think it's 10-dimensional, it's 10 inputs, 10 timestamps, 1, 2, 3. Yes, 10 blue squares. I process them with a kernel of size 4, and I did padding valid, which means that at the moment I arrive at the end of the sequence, I stop. And this gives me 7 outputs. And the 7 outputs, then I can use like a max pooling of kernel 7 times 1. And this means that for each of the kernel in the convolutional network that I put in, I obtain a number. And then this is one of the orange squares that you see at the end. And then if I put many filters, I would obtain many numbers. And so if you think about this and you compare it with, what is it? With this, where when we said, what was it? Yes. With this, where we said we have many units and then each unit is translated into a number, it's effectively the same kind of tensor processing. So you start from a sequence, go there, start from a sequence, and then you specify n objects, and you get in output for a sequence n numbers, okay? Except that the processing here is completely different. There is no concept of memory. There is no learning across the entire sequence, but there is a local, there is learning across first neighbors because of the kernel size, okay? So advantage is for convolutional networks, the processing is parallel. It's a convolutional network, so the processing here is parallel. There is no sequential processing. There is no dependence. It's a feed-forward neural network. There is no dependence of like the last kernel from the first kernel output. And so, for instance, on a GPU, you can speed it up by parallelizing the thing. So it's faster. The cons, of course, is that you're not learning across the network. There is a question.
Hello, can you hear me?
Yes.
Okay, so very good. So my question was, what is this index I that you have in the W?
It's the index across the squares. So it goes from 0 to 3. So my four-dimensional kernel will have a weight for each channel per channel. Then this weight will get. So it's like yesterday, the 3x3. You remember that yesterday for each channel we had the 3x3 image, right? So you will sum across the 3x3 cells of your kernel. You will do a element-wise product. Then you would sum across the 9, and then you would sum across the channels. Then you would add the bias, and then you would apply the activation function. Here is the same, except that the sum over I doesn't go on the 2 dimensions, but it only goes on the 1 dimension.
Okay.
Is it clear?
Yeah, maybe I need to think about it again. But I mean, in the formula, there's no other I. There's just the Y for the.
No, in the W has the I.
Yes. Okay.
Yeah, sorry, the X also should carry an I. You're right. Right.
Okay. Okay.
Yeah, you're right. I will fix it.
And then
Yeah,
the other
because
thing.
yes.
So if I understood correctly yesterday, I mean, one of the large things about the convolutional networks is that that they are translational invariant, so, which is why we like to use them. So here we have this again, but here I don't see why translational invariance is relevant to the.
No, here is not relevant. It's true. It's not relevant, and there is no reason why, if you have a time series, you would process it with this. And in fact, it came as a surprise. I think that it was a paper by Google that proposed this. So they basically try to approach natural language processing with this. It's not obvious. There are pros and cons. The pros are extremely computational. So these things are way faster. You will see later when we do the endzone, the training a convolution, 1D convolution, it's way faster than training a recurrent network. There is no real conceptual reason why you would do this.
Okay.
I would say. At least I don't see it. Then maybe those that push for it have something in mind. Effectively here, you could consider to say, okay, I want to read I could read the sequence at once. So if you have a sequence of 10, you could say that the kernel is 10 times 1. But then effectively, that's like a dense neural network, okay?
Mm-hmm.
There is another thing that, so this is not the only place where 1D convolutions is used. Yesterday, I barely mentioned it, that one of the big architectures, the big convolutional architectures, use the 1-by-1 kernels. And 1-by-1 kernels in 1D or in 2D convolutional networks are very frequent these days as a way to do pre-processing of your data with a neural network in parallel. So imagine, take the example of our problem. We have PT, eta, phi being the particles be the inputs that characterize each particle. You might decide that PT, eta, and phi are not the things that you want to feed in the whatever network you're doing after. You decide that instead you want to use some basis transformation, a non-linear basis transformation. So you want to feed your network, whatever your network is in the output. It could be convolutional, dense, recurrent, whatever you want. You want to give it in output, in input, a set of functions of your initial representation. So PT, eta, phi in our case. So a way to do that would be you take PT, eta, phi of a particle, you apply some dense neural network that gives in output, depends on how many nodes you put in the output layer, some certain number of functions of PT, eta, phi. Then you have a theorem that says that you can basically learn any smooth function of PT, eta, and phi with this processing, and then you're happy. Now you take this network, I give you the data, and what you would have to do is that you take the first item, the first particle, you apply the network, and you store it. You take the second particle, you apply the network, and you store it. The third particle, you apply the network, and you store it. And this sequential process is slow. So what you would like to do is instead is to take all the particles together and apply the very same network to all of them. Mm-hmm. And the practical way of doing that, if you think about it, is instead to use a convolutional 1D with a 1 times 1 kernel. Because once you move to a 1 times 1 kernel, effectively the sum over I gets away. There is no I anymore because you're processing one particle at a time. You sum across the channels. You apply that function there. So it's sum over C of WCJ XC plus BJ, and then activation function. That's exactly the math of the dense neural network that you do it particle by particle, but you use the implementation of convolutional network on a GPU, which parallelizes completely the problem for you. So wherever you have a problem in which you think that the first stage of your processing should be some reshuffling of the input information in some function of those, the architecture you want to use is a one-dimensional convolution with a 1 times 1 kernel. And for instance, this is used in the CMS and Atlas B-tagging algorithms, which were the first algorithms using deep learning, use this kind of trick. Okay, so this is a parenthesis that I want to mention to explain you why something that was introduced to do this effectively became a more generic and general ingredient to neural network architectures. For instance, we use something like this for graph networks as a pre-processing stage. Okay, this was a little bit of a parenthesis that I thought it could be important. There is a question. What is the end that was left? Yes, it's the end that was left. So that's the summary, and then we go to the endzone part. So we discussed this recurrent neural networks architecture. As I said, it's not really the kind of thing that obviously fits the kind of data that you have, for instance, at a collider. It's more useful for other things. You could imagine this kind of networks to become eventually relevant for, I don't know, gravitational wave processing, where you have a time series. People use them sometimes for, like when you want to detect supernovae, you have an image of sky, and then you're looking at it as a function of time and see something that goes on. So time domain kind of astronomy. But for particle physics, it's a little bit of, it's not a clear connection, but the underlying parallelism is between natural language processing and trying to understand the physics of, for instance, of jets. But then I showed you also that could be used also for more generic problems like full event topology identification. Now, there are pros and there are cons. The cons is that, as I said, you need some ordering algorithm. But if you have an ordering criterion at hand, it's not really a negative thing. The pro is that you can handle variable length sequences. You can handle them abstracting away from the irregular detector of geometry. And so in some practical circumstances, they could be a good choice. And then I showed you that a very similar thing can be done with 1D CNNs, particularly if for the kind of problem that you have at hand, you don't think that you really care about the information flow across the full chain, but only on local features, let's say. The advantage, it's more on the processing aspect because it's completely parallelized, also it's way faster. And as a matter of fact, if you look at the practical applications, it gives you okay answers, but it doesn't outperform LSTMs or GRUs when LSTMs or GRUs are used. This was the last slide.
There is a question.
Just a question about this one-dimensional CNN. Why is reshuffling our input variables a good idea of pre-processing?
Sometimes you want to allow the network, the downstream network, to handle functions of your inputs. It's an idea that somehow it's taken directly from previous phases, previous eras of machine learning. For instance, support vector machines. Support vector machines are a linear kind of classifier but linear on kernels, and these kernels are functions of your inputs. And basically, you try to optimize the kernel. And here you are basically using the the universal learning power of of a dense neural network as the ultimate way for you to to learn which is the right kernel. But the fact of taking your inputs, processing with some kernel, and then do the rest of the processing on the output of the kernels is pretty much a standard way, for instance, in computing vision. And so, for instance, in computing vision, you might want to decide that it's not, you don't want to learn by R, G, and B separately, but you want to learn by some function of R, G, and B, and you want to learn in the process which kind of function you should be using. But for instance, if you imagine like filters that people like, and written filters that people apply on images, this is what they're doing. Like they take R, G, and B, and then you apply some mathematical function to the R, the G, and the B, and to manipulate the image. Here, the manipulation is something you want to learn in a training process. And to do so, you want to do it pixel by pixel. It's not something you have to do, but it's often is helpful. The advantage is that, the big advantage is that you want to apply the same processing to each pixel, and typically this translates into a very small number of parameters. In principle, you could learn the very same function just taking all the pixel in input and give it into a gigantic dense neural network. But the fact that the network will learn that each pixel should be processed with the very same function, and the very same function is explicit that one, would be extremely hard for me to imagine that the training would converge there. So if what you want to do is a pixel by pixel processing, you should write down in the architecture that the pixels should be processed individually first, and then whatever you learned, it should be processed after. You don't have to do it, but if you want to do it, this is the way. I don't know if these answer the question. I assume so. So I'll now close this. And we do the same as usual. So we go on GitHub. And so now there are two things which are called Notebook 4. One uses the conv1d and one uses the RNN. So I will start with the RNN. So runtime, I'll use the GPU. There is no real reason to do so. Just do it because I usually do it. But I'll leave you to an exercise to you to try. So try the exercise once, like take a recurrent network and try to train it on a GPU as opposed to on a CPU. CPU means that basically you here, you put known. If you do known, you stay on the CPU. And just measure how much time it takes. So since the processing is sequential, there is no real advantage in parallelizing at the GPU. There is a little bit of an advantage, but typically the time it takes to train a recurrent neural network on CPU and GPU is comparable. And this is also the reason why people manage to come out with deep architectures much earlier with this than with convolutional neural networks, in the sense that this is still manageable on a CPU, while a CNN would be completely unmanageable. And that's why, if you want, the deep learning era of recurrent networks started in 95 and not in 2012. Now, if you open the other notebook, it's a convolutional 1D. It's better than a 2D, but still there the GPU gives some advantage. Now, the first cells are the usual one. I just wanted to say some word on the data format. So we briefly saw this yesterday. Still doing stuff. So the data that we're reading in is a sequence of particles. We're playing with the sequence of particles today and tomorrow. It's PT ordered. Today, this is relevant because, as we said, we want some order. In tomorrow, it's not going to be relevant because the network doesn't really care. The network of tomorrow. Now, the list. So this is the same line of yesterday that defines the target. That part doesn't change. The new thing is that in this one here, we are loading the jet constituents list. The jet constituents list is formed this way. There are 100 particles, and each particle has 16 features, which I printed somewhere. I think it's in the other one. Damn it. Yeah. I mean, I will show you the list later, but basically it's the 16 quantities are functions of pt dan phi. They are pt dan phi, px, py, pz, pt dan phi relative to the jet axis. It's very redundant information. And the reason why I use 16 of them and not just pt dan phi is the thing that I told you at some point, is that there is a practical advantage in giving more linear functions of your inputs in order to improve the learning. But you could decide to just cut the sequence at the first 3 entries and redo it, okay? Then the network itself. So you see here that what I do is that I start from a GRU unit, so a GRU layer with 40 units, and activation, I use a hyperbolic tangent, and the recurrent activation is a sigmoid. So this is exactly the kind of stuff that I showed you in the lectures. You could change these things. You could, for instance, here you could use a hard sigmoid. So as long as you have the same kind of behavior, so this should be an activation function between 0 and 1, and this should be an activation function between -1 and 1. Okay. And then, oh, I forgot to run this. So you see that I'm reading this sequence 100 times 16. I have 40 units. And so the output is 40 numbers in a one-dimensional array. Okay, there is the usual dropout. And then these 40 numbers, I just directly put them in a dense layer. So in this case, if you want, the feature engineering part appears to be a single layer, but remember that the GRU has a multi-layer structure inside its so you cannot capture complexity through the complex architecture that is within the unit. And then the rest is the same. And you also see that there's pretty substantial amount of parameters, okay? Because remember that all the products that I was discussing before, these are parameters that are tunable. And then you can train it, and this I think will take a little bit. So while this goes, I don't know if Colab lets me do it. I think so. I want to show you the other one. Unless there are questions. So, and I forgot to say, here you can change, as I said, you can change the activation functions, fine. You don't have so many degrees of freedom if you look at carets of what you can say. And remember, this is something which is between -1 and 1. This is something in 0 and 1. You can certainly change this. You can change the dense part of the network the way we usually do, so activation, number of nodes, and so on. But another thing you can change here is that, for instance, here you can put an LSTM, or you can put a simple RNN. this is something that you should try, and you should see which kind of performance you get. Okay. The other data set, the other notebook is exactly the same, except that this time, when we read this kind of input, now we are interpreting this as a one-dimensional sequence of 100 items with 16 channels. Okay? So in this case, the network is different. It has a conv 1D, 20 filters with size 3. So I'm reading 3 particles at the time. Channel last, because 16 is last. Strides 1, which means that I'm shifting by 1 slot the 3 cells, the 3 slots kernel. Padding valid, activation relu. The rest is the same. And here you can really do the same kind of stuff we were doing yesterday. You see that I put the activation directly here. You could decide to take it out, put a batch normalization as we did yesterday. I took a little bit of a shortcut here. And also I used an average pooling rather than a max pooling just to try something different. But again, this is something you can try to change. And the pool size, I use the same number, but there is no reason why this should be the same number. This, I mean, this is just, you could put 2 here if you want. Now you see that I have 3 of them. And so let me just put this by hand so that I can run it just to compile the model and show you the compiled model. And here I didn't say that, but this, I never changed this. So I'm trying to solve the same kind of problem. So categorical cross entropy, Adam, but again, these are things you can change. So you see now that I'm starting from the 116 and I'm processing with 3 by 3. And then I get to the end, I stopped as soon as I arrive at the end of the sequence. This means that the sequence is cut from 100 to 98 because I'm using the kernel size of 3. And you also see that rather than the 60 channels, now I have 20 channels because I use 20 filters. Then I do the average pooling, and the average pooling is divided by 3. Now 98 doesn't divide by 3. And so you get the extra one. So it's 32, the output dimension. And then I have another one, which is the conv 1D, that again, processing with kernels of 3, so you get 30 in output, but now you have 40 channels because I put 40 kernels. And then 30 now divides by 3, so you get exactly 10. And then after the last conv 1D, which is size 3 again, no, size 2, I get 9 outputs. And then I have a pool size 9. And so out of these 3 layers, my sequence is turned into a single number, but I get 60 numbers because I have 60 kernels. Okay, and then these 60 numbers, I flattened them into a one-dimensional array, which means I'm removing this index here, which plays no role. And then I process everything with a dense neural network that gives me the 5 outputs. And again, you have the first part of the network up to here is the feature engineering. It returns 60 quantities that then you process with a dense neural network and you obtain your output. Okay. Now, I mean, I would not run it because you can run it yourself. There is no really, this is still going. You see, it's pretty much slower. I'm not sure if I can run 2 of them at the same time. Maybe I can. And here I have the printout. These are the features. These are the 16 features where I have px, py, pz, energy relative to the jet, so the fraction of energy carried by the particle with respect to the jet energy, pt, relative pt, eta, relative eta. There is eta and phi rotated. I explained yesterday that people sometimes like to rotate the image or the particles, if you want, in such a way that if you have something which is elliptical, it's aligned vertically. And so there is a paper that was describing this rotation, and we apply the rotation. And same for phi, delta r, cos theta relative, and the idea of the particle, so which kind of particle it is. And okay. I forgot to put the runtime. Yes, so I'm running on a CPU. It's not super slow, but it's not super fast. Okay, this is gonna take a little bit. So if you have questions, it's a good moment to ask. There is one question.
Hi, I just wanted to ask if there's an effort people try to invest into interpreting the pre-processing that the network gives you. So, I mean, is there a way to understand why the network selects certain features over others, or is this really difficult to see?
It's difficult to get the why. Okay, in the sense that why an answer to a question that is why is this relevant has to do with domain knowledge. And somehow I would say that the kind of thing you want to do is the other way around. So in the sense, you could ask yourself the question like, what did the network learn? And based on that, if what the network learned is not obvious to you, you might be learning yourself something. So to give you an idea, this is an exercise that we didn't do, but whenever you see a network that, so the physicist way of doing things is that you start from high-level features because you have a physics intuition of the problem, so you know what is relevant in the problem you are handling. So you say, okay, this is my basis of relevant information, try to get the best out of them. And this is what people have been doing for decades, okay? And these things work pretty well, okay? Now, if you find a network like we did that starts from the raw information and improves on top of these quantities, the one thing that you would like to do maybe is to go to break. Now it's difficult to do it with Keras. Well, PyTorch and TensorFlow, it's easier because it's really a tensor manipulation. So for instance, you could, while you are doing the full method, you could stop here and retrieve the tensor produced at this stage, which is like these 60 quantities. And you could start to correlate these 60 quantities, like you make correlation plots of these 60 quantities with the physics quantities that you think are relevant in the problem. And sometimes you would learn that the network is learning something that you know, which somehow is interesting from the point of view of the computer scientist, because, okay, the network, it's an artificial intelligence achievement, if you want. The network is learning some physics out of this problem. Typical thing that happens, if it's a jet classification, you will find one of the 60 quantities typically is very correlated to the mass. I can actually show you that. We did this exercise on this very same data set for the graph nets, from the one that we're gonna see tomorrow. And the structure is the same. So there is some graph neural network processing that produces a given number of features. And then I'll show you this. Okay, this is a little bit of the lecture of tomorrow, but so you have some processing that is happening. Tomorrow we'll discuss this. At the end of this, you have this matrix that has a certain number of features times the number of particles, and then we sum across the particles, so we extract DO quantities, okay? So these are the high-level features. If you take these quantities and you correlate with things that you know are relevant for the problem, start to get things like this. So for instance, this is the correlation between the first of these quantities and the multiplicity of the particles in the jet, the substructure quantities of the jet, tau1, tau2, and tau3. Tau1, tau2, and tau3 are the quantities that are so far used by CMS and Atlas to do this task of jet classification. And these are the 5 categories of the jet. And you see that if you look at the correlation coefficients, you say that, okay, there is something happening here, but pretty much O4 is tau1. And to some extent, O2 is strongly correlated to tau3, not that much maybe, but the first two are striking. So O1 was learning the jet multiplicity, and O4 is learning tau1. Now, this is telling you that the network is learning something meaningful, and you can make this kind of analysis. You should make this kind of analysis every time. Then people are lazy, me included, and we don't do it. But the interesting thing is the other way around, which is when you find some of these quantities which do not correlate with the things that you believe are relevant in the problem, it means that the network is learning something that you didn't think about. And there, and this is where the difficult part of the exercise comes in, there is a way for you to improve your knowledge and then maybe derive some analytically defined quantity which has some physics meaning that correlates to that quantity there, and maybe you will learn some physics out of it. So this is the dream of everyone, if you want. But we're not there yet because nobody is really doing this exercise. I mean, we are at the stage that we are proposing still how this technology could be used in the next run of the LHC, for instance, but only when these things will be used with real data, people would take the time to do this exercise, and this is where we might learn something.
Thanks.
I think this thing, the RNN finished. I don't know if you are trying this meanwhile. The RNN finished. I mean, you see that I don't remember what we had yesterday for the CNNs, but it's pretty much what we saw for the other ones. I used to look at this 30% line, and this is for the W and the Z, it's way worse than what we used to have with CNN. With the CNN, we used to be here. So it's an order of magnitude worse for W and Z. While for the top and the gluon, I think it's pretty much the same. This other one, still going? No. It's more or less the same. Yeah, slightly better. No, it's substantially better for the quark and slightly worse for the gluon. The picture you see is the same. Now, I don't remember what we had for the conv2D, but I think this is worse than what we had yesterday. So this is pretty much it for today. I mean, we still have 10 minutes. So first of all, you should keep trying and see if you get something better. I think these results are pretty easy to beat, I would say. Not necessarily with these architectures, though. And then if you have other questions, you can also take the time to answer those. Yes?
So maybe this is a stupid question. So I just ran the RNN example in parallel to you, and somehow for me, basically all of the quantities are 10% worse. So is there
Worse.
something? Yes, is there something? I mean, is this so probabilistic? How good the AOC?
It is. It is. In fact, if you look at the RNN is particularly bad in that. So if you look at this, you're seeing my screen, yes. So these are the ROC curves. This is different format for the plots because it's for one kind of jet. Like, for instance, this is the gluon. But then you have the different architectures. So we have the DNN of the first day, the CNN of yesterday, the GIU of today. This is not exactly the same architecture, the same kind of model. Then the architecture is way, way bigger here. And then these two guys are those of tomorrow, okay? And now, if you see, like if I zoom, can I zoom? No, can I zoom? So when I zoom into one of those, you see that these are bands. Okay. Okay. Some band is wider. Sometimes some band is very, very small, like the line. So what are these bands? So what we did was we took our data set. This is something which is called cross-validation. K-fold cross-validation. So we take our data set, and rather than doing test, train, and validation, we split the data sets in 10 parts. And we train 10 times using 9 parts for training and 1 part for validation. And then changing which is the validation part at the training. So if you have 10 parts, there are 10 ways you can do this. And then here we are showing the mean and the RMS and the spread, the RMS in this case, around the true positive rate as a function of the false positive rate. And what you see is that even for such a bigger model, the RNN is particularly noisy. Now, 10% is a lot. It might be due to the fact that we have a very small data set. But somehow this seems to say that in some sense, this architecture is more data eager. And so it's more noisy in the training. The reason why you get different results is because everything is randomized, and particularly the initial set of the weights that you're using. So the starting point in your stochastic gradient descent is random. Okay. Does this answer?
Yes. So do people normally in the paper, do you have a seed for your random number generator so that people can
use a seed? I prefer to run this. So I prefer to have a random to randomize the starting point, but to do the training n times and quote an uncertainty around the AUC and the rocker. And when you see like in the RNN, so the focus of this paper was not the RNN line. The focus of this paper was the purple and the red lines, so the best on the graphs. But if the focus of this paper would have been the RNN, I would not have considered that a good training in the sense that it was still too much noisy. At the end, the only thing that I wanted to learn from this plot was that the difference between the orange and the purple was significant. It was not like a random fluctuation thing. And given the size of the bands on the two lines, this is a significant improvement. And so I was happy with that. But if my focus was, I don't know, the difference between the green and the orange, and then you see that I would have had to do more effort there, okay? Which means typically use more data in this case, I would say. And there is a question by Anne-Catherine.
Hi, yeah, thanks. I was just wondering, so both today and yesterday, I tried adding another dense layer to my networks, and both times the accuracy went down, and also the loss function, or the loss didn't reach the point that it did without that extra layer. Is that pointing to overfitting, or what's going on there?
I would have to see the. I will need to see your training history plot, but to understand if it was overtraining. So you added one layer. So typically, so it depends on how you did it. So you just added one layer with the same size. What did you do? Do you remember?
Yeah, so in this case, I added a dense layer in between the one of size 20 and the one of size 10 with a size 15. I kept the activation the same and the dropout rate the same.
That's very weird. And it didn't improve.
No, yeah, my accuracy was definitely worse. And actually, interestingly, the W tagger specifically had a really weird shape. It like the rock curve sort of had a sharp cutoff at looks like about 0.7.
The sharp cutoff happens sometimes if the so basically if you run out of events. So in order to debug that, so when you see something like that, sometimes it happens. The first thing that you should do is that rather than, so once you have the, let me show you the code. Once you run the, so this is the target, right? This is the target. So we never looked into this code, but the rock curve, I'm using some standard library to make rock curves out of scikit-learn that takes two inputs. It takes as input the target and the prediction. And the prediction is this tensor here, which I obtain running model.predict on some validation data set. So when you do model.predict and you obtain the prediction, you could actually make histograms of this prediction. And what causes this sharp drop in the AUC is typically at some point you run out of statistics and the algorithm here is not smart enough to understand how to sample points across this curve to make a curve smooth. So it's somehow a drawing artifact that could actually be originated by the fact that that specific model didn't succeed in making score values which were populating the right or the right or the left tail. So that's one problem, I think, that sometimes so what happens that you try to run again, it disappears, and it's a plotting artifact. Sometimes there are ways to intervene on this function and to say this function to sample on like regular points here, such that, because this is basically connecting dots, and if there is no extra dot, it just drops down. That's one thing. The fact that you add the dense layer and it doesn't get better is a little bit suspicious. So I would have said, so typically this happens when you really saturate it, so there is really not much more for you to learn, which could be the case because this data set you're playing with is very small. On the other hand, I would be, so if you have the architecture that you used and you could just put it on Slack, maybe I'll try to give it a try with the full data set and see what happens.
Sure, will do. Thank you.
Basically, our time is over. I don't know if there is one last question. Otherwise, we...
Moment, I don't see any. In any case, this evening we have the discussion session. So if there are other questions on this lesson and the other ones, of course, of yesterday or Monday, we can discuss them in the discussion session at 6:30.
Yeah.
So.
I will have my daughter with me, so let's see how it goes.
It will be more fun.
Yeah, I mean, she's 10 months old, so it's gonna be complicated to convince her not to cry if she wants to. But okay.
Okay, if there are no other urgent questions, we can thank Maurizio, and we see each other again